produce my two C's. And that's it. It's as simple as that. So what shall I call the thing that the two B's react to produce? W. All right, fine. W. So I say that B plus B produces W, and then W plus A produces 2C. Now, does that work overall? Well, yes, it does, because that is used up. So that's produced, but then it's used up. So overall, I've used B and A, and I've produced 2C. Now, that corresponds to the stoichiometric equation here. A plus 2B equals 2C. A plus 2B goes to 2C. That corresponds to the stoichiometric equation. But actually, it also corresponds to the rate equation as well, because what it means is that this step here is the rate determining step. And this step here is a fast step. So this is much faster than this. Oh, it doesn't have to be much, but it is faster than that. And so that is how you construct, basically, I mean, that's the example of how you construct a mechanism based on the rate data that you're given. Now, I mean, I could go through lots more examples, but I think the best thing is probably for you to do questions and to work on those. Okay, hopefully I've given you a vague idea there of how we do it. Now, I haven't finished, hang on, sorry, because I've got to do activation energy. I did say we've nearly finished, we have nearly finished. We'll be finished by 5, but not before, I don't think. But first of all, I just want to make it clear the difference between the order of reaction. That's not wrong. The order of reaction, I want to make the difference between the order of reaction and the molecularity. Because sometimes they ask about molecularity. So what's molecularity? Anyone know?
The number of species taking part in the specified step in the reaction. Leslie remembered.
No, hang on. What did you say? Total particles
a total number of so if it's A to B, molecularity would be 3.
If it's in the rate determining step, yes.
If it's in the rate determining step.
So it's the molecularity is the total particles in the rate determining step. So for this one, this example here, we would say that the molecularity here in the rate determining step is 2. There are 2 molecules, and the molecularity of B in the rate determining step is 2. Okay. But I just want to give you one other example because sometimes this can be a bit confusing. So let me take a completely different example. Let's supposing I have some X reacting with some Y, and that produces A, okay? And then A reacts with Z, and that produces the product. Okay. Now, supposing here that this is the rate determining, this is the rate determining step, and that this is fast. Okay. Now this can be a bit confusing because how would I write my rate equation here? Well, I'd be tempted to say the rate equation. If I did an experiment, what would I find? I would find that the rate equals the equilibrium. Sorry, the rate constant. The rate equals the rate constant times the concentration of hang on a minute, the concentration of A and the concentration of Z. Well, there's a problem there, isn't there? Why?
We don't know what Z is.
Because
A isn't one of them.
A is not one of the reactants. So that cannot appear in the rate equation because the rate equation can only contain reactants. So what do we have to do? Well, what we have to do is we have to say, hang on a minute, okay, the concentration of A is really important, but where does the concentration of A come from? Well, it comes from the concentration of X and Y, and so actually, X and Y have to appear in the rate equation. And so the overall reaction would be X plus Y plus Z goes to products. That's my overall reaction. But in fact, the rate equation will be first order with respect to X, first order with respect to Y, and first order with respect to Z. But look, what is the molecularity of the rate determining step? 2. The molecularity is 2, but actually there are 3 species in the rate equation. And you have to watch out for that, because I have seen them put that sort of thing onto a paper, and sometimes people are completely thrown. Okay. The last bit is that the rate is first order with respect to x, first order with respect to y, and first order with respect to z, but the molecularity is 2, because there are only 2 species in the rate determining step.
So
Yes?
in that case, wouldn't the... This is going to sound stupid, but
No,
wouldn't the first thing be the rate determining step, because it's determining whether you can react or not? It's like, you need the A to react, so...
Well,
isn't
in a
that determining
sense,
the rate?
this is, though this may be fast, but this does have an effect on the rate determining step, and that's why these concentrations are important, because the concentration of that depends on the concentration of these two, and the concentration of A actually influences the rate equation, or rather the rate of reaction, sorry, and so therefore the concentration of these two is important, are important. So yes, in a sense you can say, it's almost as if this whole thing is one step, isn't it? In this case. So yes, I mean, I see...
But how is it different to the other one? Because why would it...
Right, well, it's different
Just
because...
because it's just...
A is
Look,
only getting used to
look,
the
this is
meeting.
important. The reason this is different is because the rate determining step comes first.
Yeah.
Okay? Here, the rate determining step comes second. So look, the only things which affect the rate determining step here are the 2 particles of B. Okay, this is the slow bit, and then this bit just goes bam straight away. This is, remember, it's a bit like our hourglass. The first gap is the very, very small gap, and so everything that gets through that gap goes straight through the rest. So everything that gets past this rate determining step goes straight through. So that's
only because of the speed, though.
Hmm?
That's only because of the speed.
because of the rate, yeah.
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 Okay.
Yeah, so, I mean, the fundamental difference between this one, really, and this one, is that the rate determining step is first here, but here the rate determining step is actually the second one, and that makes a big difference to the overall rate equations. Okay.
So in the exam when doing a mechanism, you've got like actual substances. Can you substitute them so you say, for example, one particular substance equals B for the purposes of the mechanism? Just
No,
so it's
I
easy
would
to
just
see.
write it out. I mean, just be creative. So if you've got, I mean, you know, NO2 plus NO2, supposing that's your first step. Now just be creative, okay, let's say it makes that. I mean, I don't know if that exists, it doesn't matter. But just make it up, okay, and then you say, right, NO2, N2O4 reacts with chlorine to produce N, etc., etc., etc. You know, that's a stupid example. Do you see my point? You just, literally, as long as you make sure the number of atoms on each side are the same, it doesn't matter if you make up molecules when you're writing an equation, a rate equation, when you're writing a reaction mechanism. It doesn't matter if you make it up. Okay, that's one of the nice things about it. It's a bit of creativity. Okay, I'm really sorry I'm going to go on a bit longer because I haven't done activation energy, have I? There's one more important thing I need to point out to you. You need to be able to do, and that is you need to be able to work out the value of the rate constant, and you need to be able to work out its units. So how would I work out the units here? I'm just going to do this one quick example. What I would say is I would say rate equals, and of course I'm taking that over to that side, so, sorry, rate constant equals rate over the concentration of those three, okay? Now, I would have values from my data, which I would then plug in, and I'd calculate the numerical value of that. Will? And how do I find out the units of the rate constant?
Take all of the units.
Put all the units together and then cancel stuff out.
Exactly. So what I do is I cancel stuff out. So what I would do is, what I've actually got on the bottom here is I've got moles per decimeter cubed, 3 concentrations, and that's cubed. Okay. So what do I do here? Well, I've got one of those on top. So what I can actually do is cancel one on the bottom, can't I? So I end up with seconds to the minus 1 on the top, and then on the bottom I've got moles per decimeter cubed all squared. So what would my units work out as? Well, my units there would work out as seconds to the minus 1, because that's on top. I've got moles squared, yes, and I bring that up to the top so it becomes to the minus 2. Okay. And I've got decimeters to the minus 6, because when you square indices you add them. Okay, so I've got because dm to the minus 3 squared is dm to the minus 6.